Okay, welcome to the course for the TA of the course Elementary Thermodynamics. So no one has joined till now. So let me wait for a few minutes and then we can start if anybody joins. Hello. Okay, it's already 4. Let me wait for a few minutes. If anybody else join, then we can start. You can unmute yourself if you have any comment to say or any question regarding the classes. Okay, let me wait for a few minutes, up to 4 5, then we can start if anybody joins. Okay, is it visible?
Yes.
Okay. Okay, so this is the basic thermodynamics course. If you go through the lectures, you will find out that this is just the graduate level course. So in this course also, we will be restricted ourselves in very basic discussion in the TA classes as well. So let me start with a basic general question of thermodynamics. Then we can gradually go through we'll go in the discussion regarding some, because in this week, mostly the lectures was on the mathematical background of thermodynamics, the differential equation, partial derivatives, these things. So in this tutorial also, we'll discuss about the question related to the mathematical equation, differential, these topics. Okay. So, by the way, first question, let me ask. Um, Thermodynamics deals with, if you have given four option, let's say rates of the equation, transformation of energies. Okay, probably it will be okay right now. So just the I have discussed this question. Thermodynamics deals with the transformation of energies, basically heat and work. And kinetics deals with the rates of equation. Probability of finding of electron is related with quantum mechanics, and this is also related with quantum mechanics. So basically, this is the Zeeman effect. Okay. So now let me discuss the numerical question related to our discussion, the lectures taught in last week by ma'am. So let me start with the cyclic rule. Okay. Do you have studied cyclic rule before?
Yes.
Okay. So in class, I found that there were the derivation of cyclic rules, so two or three steps in between. It was not provided. That's why I thought that let me just discuss the cyclic rule. That let's say the formal derivation of the cyclic rule, or basically it has a formal name. Okay, do you know that? What is the formal name of the cyclic rule or cyclic chain rule, whatever it is? It's actually the Euler's chain rule. Okay, this is the Euler's chain rule. This is not Euler's. Euler's is the right pronunciation, I guess. So let's say this is
Euler.
the Euler's, because in our BSc time we also pronounce it like Euler's, but later we know that we came to know that this is Euler's basically. Just like you know the this, what does it pronounce?
De Broglie.
No, oh no, actually this is Dabroy. The right pronunciation of this is Dabroy, not Debogli. Okay, we made it according our local language, but this is actually the Dabroy. So let's say f is a function of xy, two variable function. Uh, when I'm saying a function x and y, what does it mean? X and y, signifies a particular quantity. This is called independent variable. Okay, because these x and y are independent, you can choose according to you. There is no restriction. Okay, choosing on particular x and y, the value of x is fixed. F is fixed. That's why this is called independent variable. Okay, so let's say f x and y, these are the two variables. F is equivalent to fx. So what will be the df? First class. If if my audio breaks, you can tell me. Okay, it is audible or not, because the mic is connected. I think 1 minute. Is it visible?
Yes.
No, probably not. What is happening? Connection has been lost. First, the storage issue, then what happens? Re- It's not happening. Then I have to join from the devices. Please wait for a few minutes. I don't know what happens. It's not connecting.
Okay.
Last time this never happens. Like two course never happens. Probably the internet issue may be there, I think. Screen is visible, right? Then why it is
Yes.
here it is showing wireless display. Yeah, otherwise I am joining from the other device. Probably there is an internet issue. Okay. Is there any echo?
Yes, a little bit.
Now?
Now also.
Till now?
Okay, fine.
Okay. So there is now no echo.
Yes,
So now let me present from here.
but screen is not visible.
Okay, screen will visible. Okay.
Okay,
Okay, ठीक. So x and y, these are independent variable, and let's say f is a function. Now, so what will be the df? There is also an echo.
echo.
Be done. It's pathetic. 1 minute. We rejoin. That's why I avoid two devices and just connect with this screen mirroring. I don't know why this is not happening today. It was connected. Suddenly it just lost.
Internet connection lost.
You know, not inter this wireless display. We are discussing. I just share my tab screen to this laptop. That's why I use this wireless display facility. But let me just restart my device once, or we can stop sharing. Probably it will work. I don't know. These electronic devices are very subtle. Like anytime anything can happen. Please sound like I can mute. I think. Then probably there will be no. Okay. If this not work, then I will do this. So this is a problem of left laptop, not my tablet. Mm. Tablet is get no, sorry, phone. My phone is get laptop is getting slow down. Now. checked everything. Everything was okay. Leave it. Probably this will not work. Okay, is there any echo now?
echo.
Okay, just help me to fix this echoing sound. Then it will be okay. Mm. Now, okay, now is there any echo? Hello. Now is
Hello,
there any
now
echo?
is there any echo?
No.
Okay.
Okay, perfect.
And you can hear
And
me
you
now?
can hear me now?
Yes.
Okay.
Okay,
Chalo.
chalo.
And let me
And
share
let me
my
share my
screen.
screen now,
Then it will
then
be
it will be fine. ओह
okay.
बेकार में टाइम वेस्ट हो गया.
Okay.
Okay, you can hear me?
Yes.
Okay, and no echo, right?
Okay.
Okay.
So
So, one minute.
now
Now
is
is
there
there
any
any
echo?
echo?
Okay.
Okay,
Okay.
okay, okay, okay. I understand. I understand. Yeah.
Chalo.
Chalo.
So
So,
what
what
will
will
be
be
our
our
DF
DF
right
right
now?
now? DF will be
Del f del x dx plus del f del y dy.
exactly when this is
Y
y
constant
constant
into
into
dx
dx
plus
plus
del
del
f
f
del
del
y
y
x.
x.
This,
This,
right?
right?
This
This we have
studied
studied,
these
these
things.
things.
This
This
is
is
correct?
correct?
Yes.
Okay.
Okay.
So
So
now
now,
let's
let's
say
say
what
what
we
we
can
can
do
do
right
right
now.
now.
Again,
Again,
del
del
f
f,
del
del
x
x,
y.
y.
I'm
I'm
just
just
differentiating
differentiating
with
with,
I'm
I'm
just
just,
okay,
okay,
let
let
me
me
write
write
it
it
first.
first.
We
We
can
can
write
write
this.
this,
We
we
can
can
write
write
this
this
when
when
this
this
is
is
zero,
zero,
right?
right?
Yes.
Then we
Then we
can
can
write
write
this.
this.
Okay.
Okay.
In
In
that
that
case,
case,
if it
if it
is
is
true,
true,
because
because
I
I
just
just
divided
divided
by
by
this
this
f
f
by
by
dy,
dy,
then
then
it
it
will
will
be
be
cancelled
cancelled
out
out
and
and
dx
dx
dy
dy
will
will
be
be
there.
there.
So
So
it
it
can
can
be
be
written
written
that
that
into
into,
I'm
I'm
just
just
taking
taking
this
this
as
as
x.
x.
Why?
Why? This
This term
term
can
can
be
be
written
written
like
like
this.
this. Okay.
Yes.
Okay. So if this is true, so now just multiply it.
But from where we are writing the first line, I
Uh,
think it was a cyclic rule.
which one?
The first line.
This line, na, we are considering a cyclic process. This is valid for a cyclic process, right?
The next line.
This line, no, 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 this is not cyclic rule. Just this is clear.
Yes.
If this is clear, now just this df, just now divided this df dy at constant of x. This equation, then what will be? This dx will be goes away. This dx will not be there. Yes,
Yes.
good. Okay, let me write it the in between step. So df was our del f del xy dx plus del f del y x dy. Now just divided this. When you will divide it by dy, then it will be partial derivative automatically.
Yes.
So, and this will not be there right now, and here dy will become. Is it clear?
Yes.
When this will come, the f will be fixed. Why f is fixed? Because this is overall a cyclic process. Clear?
Yes.
So now just rearrange this equation, then you will go get this. When you rearrange this, then from there you can get this. From here,
But there is two del f del y at constant x.
no, this is 0, right? You have to take
Yes.
it. This is 0. So when you just rewrite it as like this, you can write this.
Yes.
Take this dy in this side.
Okay, I got it.
Okay. So this is okay. I thought you misunderstood that part. This is trivial. From here you can write it just taking this side and just by dividing the x. And this is valid when we are considering a cyclic process. That's why it's called a cyclic rule. Otherwise, it will not be valid.
This is cyclic process, so the df is 0.
Obviously, in a cyclic process, you can think like that, na?
Yes.
You have to make the df 0. It is in fact very small, so that it will be 0. And in cyclic process, for a cyclic process, when you coming from A to B and again B to A, then it will be overall change will be 0. Correct? Although there is a formal mathematical proof, this is not also formal mathematical proof because we are using this fact. This is not a just dividing. It is not x by y equal to 1 by y by x. You can't write like this. This is not that thing, but we are. This is also valid. These all rules we are using, these are valid for exact differential. So as f is an exact differential, as long as f is an exact differential, we can write this. So that's why this is a very limiting condition, not valid always, but in case of thermodynamics, for our discussion, it will be always valid. Because we will be always dealing with the exact differential basically when we are talking about our system properties, system observables, not the path function like work and heat. Otherwise, the entropy, enthalpy, everything will be a state function. So that's why it will be an exact function, and this rule will be followed easily. Okay, this is that's why this is called cyclic rule. Just
In the
check it.
second line, it is 1 or minus 1.
This is
In the second line. Next line.
this will be minus one, obviously. Obviously, it will be minus one. From there only this minus one came, no? Okay, is this clear? Is there any doubt?
Yes, but is this not the correct proof?
No, this is not correct proof. This is just formal proof because in mathematics, I will go in the Euler's formula. There is Euler's formula that is very relevant in this case. As long that formula is valid, you can do these all things. You can see while proving this, we are not using that Euler's rule. Okay, in next question I will discuss that. As long as that Euler's formula is valid, we can say this is correct. Okay.
Okay.
Okay, so going to the okay for here we can discuss few more example of cyclic rule so that it will be more clear. Let me just discuss. So how we can remember this rule? Just draw a cycle like f is a function of xy, right? Because this is very important. It is confusing also. It is very important to remember the order. Order is very important to remember.
This order is important.
Obviously, no. I want to mean that you can take this here, but you can't write dy df. See here, there is no dy df.
Yes.
Dx df is there, so that is very important. While using this, you will face the problem because in my case also I faced. So there is a trick basically. That's why I'm saying this. Let's say f is a function of x and y. So the first will be you have to write x and y or y, whatever you want. That you can write. Let's say I'm writing it like yx. You have to fix one form, one conformation, then we can apply the rule. So if f is a function of y and x, then draw a cycle like this. What will be your first term? Just first term will be f, y and x. You have seen from that cross product also, there is also this kind of rules, right? You have
Yes.
seen this? The same rule.
Yes.
Here also the same rule will be there. So here we df, dy. This is actually del f, not d. Del f, del y at constant x, the first term. What will be our second term? It will be start from here. Del y,
Del y, del
del
x,
x,
constant
f, and next del x, del f,
del x at constant y.
y. So it's very easy right now, right? So you have to remember this cycle. Or you can write like f, x, y, then also it will be valid. That is not wrong. If you write this like, if you write like this, f, x, and y in this fashion, then also it will be valid. What will be then? It will be del f, del x, y. Correct?
Yes.
Then del x, del y, f.
Then del y, del f.
Del y, del f, x. This is also valid. You can show it from here as well. From here you can do it. Just you have to apply this form that del f del x y equals to 1 by del x del f y. These things you have to apply 3 times and it will be again minus 1. Just see, this is just reversed. These two terms reciprocal.
Yes.
These terms are reciprocal and these terms are reciprocal. So eventually it will be 3 times 1 by 1 by 1 by 1. So it will be minus 1. Is it clear or I have to do it explicitly?
Which thing?
Okay. From here, from this is the cyclic rule. This is also cyclic rule. These two are the same rule, same thing, same equation. Is this clear or I have to show it?
Yes.
Clear, na?
Yes.
Okay. Just what we have to use. We know na del x del y for any partial derivative. It is 1 by del y del x. So in 3 cases, these can be replaced by this 1 by this by using this formula. This can be replaced by this using formula 3 times it will be reversed, inversed. So there will be 3 times 1, so again it will be minus 1. So you have to stick one form, either this or this. Just you write by your own and then just you have to complete the loop. The f x y, x y f, and y f x. Just like this. So that's why I'm saying it is very important to remember. This is the trick, well known trick, and it is valid everywhere.
Why it is minus 1?
This is
It is
came.
going in the clockwise direction, so it should be plus one. Anti-clockwise minus one.
No, no, no. This is not actually. This is why this minus one coming. This minus one coming from this condition. Just see, this was plus. When you took it in this side, that became minus, right? So this minus is an artifact of this condition that when this is a function of two variable, derivative is just additive. That is the problem. Okay, you know na,
Okay.
x dx plus y dy, derivative is additive. So this
Yes.
minus one is a consequence of that additivity of the derivative rules. Okay, so you this is invariant whether it is clockwise, anti-clockwise. Okay,
Okay.
because you may think that in this case this is just clockwise direction. Let me now draw it anti-clockwise. What will it give? If it is anti-clockwise, then this will be del f del x constant y. This is then del x del y constant a. This is then del y del f so this will be again minus one. There are three terms now. If there are because there are three terms, it will be always minus one. But this is actually the artifact of this plus sign. This plus sign becomes a minus here because you have taken this term this side. So this is very general. It will not be changed according to your condition. Okay. There is no echo, na? I'm just checking.
No.
Okay, because I have to upload this also. And recording is also going on. Okay. So now the third question. Just I am going to discuss few examples of the cyclic rule. Let me move it a little bit. Okay. Okay. So just consider this is just an example, not a new question. Example, okay. Pressure. Pressure will be function of pressure will be function of
Force and area.
yes, you are correct. You are correct. No, but force and area that is not true because for my macroscopic system you should know this because last time you also did this statistical mechanics course. Macro state. What is the macro state? This is a let's say a gas in a piston in a jar. So it will represent a macro state, right? And a macro state is represented by pressure, volume, and
Volume, temperature.
temperature. And these three macroscopic variables are related with a universal equation that is PV equals to nRT, linear equation, PV equals to nRT. So, in this equation, PV equals to nRT, there are how many variables are there?
P, V, and T.
No, N is also a variable.
For open system.
No, here is not open system. Variable. No, 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 no. You have to don't confuse with the statistical mechanics things. Here I am take you. Let's say you can take the n according to you. Na, there is no restriction. You can take 1 mole of gas, 2 mole of gas, 3 mole of gas. The initial condition I am saying.
Okay,
Okay,
then variable.
then variable. So, but we don't consider n as a variable. Why? I have also written here p, v, and t. Why there is no n?
Because the number of moles is not changing with time.
No, not changing. It is not changing with time. Okay, okay. Just understand these basic things. This is very crucial to understand. We are discussing thermodynamics. Although they are dynamics, it is not actually dynamics. This is also taught by ma'am. What does it mean? Dynamics क्या suggest करता है? What is the significance of dynamics? Dynamics means anything, any property changing with time. Okay, but we are discussing the equilibrium thermodynamics. Okay, Equilibrium thermodynamics deals with the equilibrium state that is not changing with time. An equilibrium state does not change with time. Okay, so it is time independent, so there is no dynamics basically. Clear?
Yes.
Then you can ask that we have studied that there is T1, 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 it is changing to T2, V2, T2, right? How this is happening?
Yes.
You have studied this in class 12 or the basic thermodynamics course.
Yes.
So this is happening, but how, right? Because I am saying that this is a equilibrium state. This is very important to understand. Just uh, actually in our time also we are confused like these ambiguous things. This is a equilibrium state. Just keep it and time goes away. Billions of years will pass. If you don't interact this system with surroundings, let's say it is not interacting with surroundings, that it is isolated system, then it will be always T1, V1 and T1. It will never be changed. Okay? So
Okay.
it is independent of time. That's why it is called equilibrium state. Equilibrium state is a thermodynamical state, macroscopic state, which will never be changed with time if it is an isolated system. But this is true for this case also. If this state kept isolated, this will also not be changed with time. It will also represent a equilibrium state. This is another equilibrium state 2. This is one, let's say, but this will also not be changed with time. This is also equilibrium state. This is a definition of equilibrium state. It will not change with the time. But in our case, in our realistic world, always equilibrium state will interact with surroundings by exchanging energy, heat, work, anything. So in that case, this P1, V1, T1 will be changed to P2, can be changed to P2, V2, T2. Clear?
Yes.
And this change we consider that because you can see here, let's say V1, T1 is fixed for our simplicity. V1, T1 is or P1, T1 is fixed. V1 is changing from V1, it changed to V2. So this change basically we consider that this change occurs infinitesimally small steps. There are infinite steps in between these. Probably let's say it was 5 liter and now it is 10 liter. Then we have to consider that this change 5 liter to 10 liter occurs very 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 slowly. That's why it's called reversible process. Okay,
Yes.
such that this is the definition because there is a contradiction. See, we are saying that equilibrium state will not be changed with time, but when there is an interaction with surrounding, the equilibrium state will change with time. Is it clear what I have said, that equilibrium state will not change with time if that is an isolated system, but actually in our real case there no system is isolated system.
Yes.
It will interact, and when it will interact it will change. Equilibrium state will be changed from one state to another state. So how it can be equilibrium state, how can equilibrium state can be changed? We are saying equilibrium state, which is by definition it will not be changed with time, and I am saying that after some time the equilibrium state 1 is changed to equilibrium state 2. This is contradictory, right?
Sir, it's become in equilibrium.
Repeat it.
We are measuring the system after achieving equilibrium.
Yes, that's okay. After, but no, but the equilibrium state has been changed. Now, this is an equilibrium state. This is an equilibrium state, but equilibrium state has been changed. That should not be. Equilibrium state never can be changed. This is our
We are
definition of
disturbing it.
we can disturb, but by definition it should not be changed. Okay, so there is a that.
Okay, so due to some technical glitch, the recording had had been stopped actually. I took the whole class, online class, and that has been taken, but Later I found that due to some technical glitch, the recording was stopped at this point. So the rest of the part which I have been taught in the class, I will again recording this part. Okay, so that's why now there is no live student, but I have to upload this also in YouTube. That's why the content which I have covered in this live class today, that I am going to discuss here again. Okay, so this part I will be recording by my own. Okay, so I was discussing this part, right? Okay, so let me just erase these things and then I will discuss this part. Okay, okay, so let's say there are two. The confusion was that what is the equilibrium state means, right? Equilibrium state means that will not evolve with time. This is the main idea. There will be no dynamics. Basically, in case of equilibrium state, there is no dynamics. Although we say the term thermodynamics, but there is not actually dynamics. No as such dynamics is there in case of thermodynamics, obviously. That is actually, the name is not appropriate, but still that's why in recent time it is stated as thermal physics. In equilibrium state means, let took a macro state. Here a macro state is taken which is characterized by PV and T, and obviously let's say first in an initial condition the state was guided by P1, V1 and T1. This is the initial state. So if it is an equilibrium state, that essentially means that it will not change with time. So first, if you consider what I have been told, that let's say if it is an equilibrium state, if you isolate the system totally, then it will be always it will be at P1, V1 and T1. It will be characterized by these three independent variables. We have discussed that a macro state obviously is guided by the is characterized by three variables. Why three variables? That I will come to discuss later, because okay. So just understand this part by part. P1, V1 and T1, and it will not evolve with time. That's why it's called equilibrium state. But when there is a surroundings, because in case of isolated system, isolated means it is not interacting with the surrounding, the system is isolated. Okay, so that's why it will not evolve with time. That satisfies the definition of equilibrium state. It's perfect, there is no ambiguity. But when it interacts with surrounding, let's say, then it will change. Obviously then it will no longer remains at P1, Q1 and T1. It will be changed. So let's say, for example, let's say let the state was P1, V1, T1 and is changed to P1 is there, pressure is fixed, or let's say temperature is fixed. It is now P2, V2 and T. Temperature is same. When temperature is same, let me just draw this. Okay, so this part, so let's say there is pressure at P1 here, the volume is actually V1, and this is at temperature T, which is fixed. I am not changing the temperature. So now this macroscopic system or macro state, whatever this is characterized by the P1, V1 and T. So we can write this state as P1, V1 and T. Now let's say now I am changing the pressure. Probably now previously it was like this, pressure was like this, and now I am changing the pressure. So when I will change the pressure, let's say I just half the pressure, from the Boyle's law that obviously the volume will be twice. Clear? So now let's say pressure is P2 and volume is V2. If it is pressure is twice, then volume will be half, or vice versa. Here pressure is half, so volume will be twice. So now the state is P2, V2 and T. Temperature is fixed. So what I am saying, this is equilibrium state. This is also another equilibrium state. These both are equilibrium state. But according to the definition of equilibrium state should not evolve with time. But that is true, obviously, when the system is isolated. But here I am interacting with surrounding, I am changing the pressure. That's why the volume is also being changed. In that case, it will be no longer same. The state will evolve. Here we can see that state is evolving from P1 V1T to P2 V2T. So that is why, so there is a contradiction. Okay, once I am saying equilibrium state will not evolve with time, and again I am saying the equilibrium state is changing from this state to that state. So where is the catch? Catch is there. To satisfy this definition of equilibrium state, we are considering the process is reversible process. That means the system is changing, obviously, but the change is very small, infinitesimally small change is there. That for happening this change, it took infinite time. Let's say, how you can understand that? Let's say P1 is 2 atm at first and volume was 10 liter. Let's say now I have just halved the pressure, obviously the volume will be now 5 liter from Boyle's law if we are considering the ideal gas. So this is the equilibrium state, this is another equilibrium state. So you can think like that, this pressure is given by, not by the weights, just I have put here a cake. This cake is giving the pressure on this piston. Okay, so now you can you have a spoon. By that spoon you are taking the cake very small amount. So when you are taking one very small amount of cake, then what will happen? The pressure will be decreased. So in each time little amount of pressure will be decreased and volume will be increased. So we can say that first it was P1, V1 and T. Next the pressure will be V1 minus dP. That's why volume will be increased V1 plus dV and temperature will be same. So in this way there will be infinite step, and after infinite step it will be P2, V2 and T. In this way the change is occurring. This is called reversible process because you can reverse the process. That's why it's reversible process. That part I will discuss later. But why this is important? Because here I am assuming the equilibrium state is not changing because the change is very small. So this is change. This is a equilibrium state 1. From here it changed, but change is very small, infinitesimally small. That's why it seems that there is no change. So this is called quasi-static process. Okay, this is not a static process, quasi-static. It seems to be static due to the very little bit of change. Okay, so that's why there is a dynamic. So actually in this way we bypass the overall analysis because there is a dynamics, obviously, because it is evolving with time, but we are considering the process is reversible. That's why the evolving time is very high, tends to infinity. That's why we can say that the equilibrium state is changing but very slowly. That is why as if it is not changing. You can think like that you have a 10 lakh rupees, okay, and you are donating 1 rupee per day. Okay, in that way what will happen? You are thinking your money is fixed because 1 rupee is negligible compared to 10 lakh rupees. But after a infinite amount of time, what will happen? That change will be very you can noticeable change will be there, and money will be decreased from 10 lakh to let's say 8 lakh. So that is another step. So 10 lakh is an equilibrium state. This is also equilibrium state. In between states are there, and we are changing this very slowly. That's why it is called quasi-static process, and that is the reason. So we can write it like this. So for reversible process, this is actually this happens quasi-statically, okay, and this is basically the equilibrium thermodynamics, because although we are changing from one equilibrium state to another equilibrium state, but we are making this change through infinite equilibrium state in between this. We are not leaving the equilibrium anytime due to the small change. That is the reason it is equilibrium thermodynamics is there. In overall this course we will learn about equilibrium thermodynamics, the relation, the equation, everything will be valid for equilibrium thermodynamics only. Okay, in that case you have to keep in mind that the process is reversible obviously, and the quasi-statically it happens. But if it is an irreversible process, let's say, which is actually the practical case, you know that, then there will be a dynamics, obviously, because that will be change with respect to time. There will be dynamics, and it will be actually non-equilibrium thermodynamics. Okay, it will be depart from the equilibrium. That will be not equilibrium state. So in this between these two equilibrium state, there are infinite steps, all are equilibrium state. Okay, you have to keep in mind that all are equilibrium state. But in case of non-equilibrium case, it is not the same. Clear? So it will be departed from the equilibrium state. Okay, so okay, let me show a figure. Okay, so let's focus on this figure. Okay, this is a BVT three-dimensional plot, because you know that a microstate is basically defined by this macrostate. These three variables P, V and T, these actually represent a macrostate. Okay, a particular system, you can say. So now you can see here this slope, this plane, okay, this plane basically, if you look at this plane, so in this plane the volume is changing its direction, temperature is changing in direction, and pressure is changing its direction. Or if you want to just, if you make slice of this plane like this way, that means in that case the temperature is changing, the volume is also volume is fixed in this direction, the volume is fixed, but the pressure is also changing. Okay, similarly, if you make the slice of this 3D plot in this direction, this dimension, this axis, then obviously here the temperature is fixed, pressure and volume is changing. So from this three-dimensional figure you can have two-dimensional plot, you know, PV, PT and VT. So here you can see, as long as this is on the surface of this plane, here you can see this is actually, this is VT, this is the VT. This is the VT, because here you can see the pressure is fixed, V and T is changing. Similarly, this for this here, in this line, PV equals to constant, that means pressure and volume is changing, T is constant, like this way. But what is the important, each and every point is a equilibrium state on this plane. Each and every point, as long as this is on the plane, it will be equilibrium state. Here what is happening, each and every point, so let's say it is changing from one point to another point, it is equilibrium state, another equilibrium state, it is P1 V1 and T, it is P2 V2 and T. So this is changing through infinite point, each of the point is a equilibrium point. Okay, this is obviously P1 minus dP, V1 plus dVt, in this way, right? Here as I've written. So this is a quasi-static change. There is infinite number of points. But when it is irreversible process, this is a reversible process. So there is a very small amount of, but then in case of irreversible process, it is actually left the plane. It will be not like this. It can be like this. It can be like this, in this way. So in that case, that is not a reversible process. That for that, non-equilibrium thermodynamics is very much important. Okay, so that's why I am discussing. So these two things are very distinct actually. So in our, obviously in our this course we will be interested in equilibrium thermodynamics only, not the non-equilibrium case. Okay, so basically thermodynamics word is valid when it is a non-equilibrium case. But here for which I was discussing that, so one thing is clear here, a macro state is obviously guided by three variables P, V and T. But is this correct or not? It's actually not correct. It's correct, but you may think this is not correct because, you know, for this we have to know 4 variables: P, V, T and N. N is a number of mole. But if you know P, V and T, obviously you can know, you can find it out what is the N from the gas equation. So actually the independent variable is important, number of independent variable. Here total number of variable is 4, equation is 1. So therefore the independent variable is actually V minus E, which is a 3. 3 independent variables are there. You can choose any 3 of them. Another one, fourth one will be set by automatically. You can't choose that. That's why it's not a an independent variable. It will be then dependent variable. So that's why you can choose PVT. Also you can choose PNT. You can choose PVN. Any 4, any 3. So there will be 4C3 arrangement. So in general, we took these 3 as an independent variables, obviously. So you can write what you can write: P equals to P of, then P will be function of V and T. Here from here you can write P equals to nRT by V. So N is not an independent variable now, obviously. So for one P, you can write P as a function of V and T. Also you can write, here I am choosing V and T as an independent variable of that state, correct? You can choose N also, NVT. It should be written like this, okay? Because 3 independent variables should be there. P is not independent variable here. P is now dependent variable, but we are taking 1 mole of gas. So if 1 mole of gas, then N is anyway constant. So it will be now, N is not a variable in that case. So it will be okay. So it will be RT by V. So you can write now our cyclic rule, right? What will be that now? As P is now function of V and T, so we can write that. So as we have discussed, we have to identify this is as P, V, T. Now just draw the cycle like this. So cyclic rule will be del P, del V T, del V, del dP, del T, del P, V equals to -1. So this will be the cyclic rule. You can write the cyclic rule in terms of V as well, because V can also be written as function of P and T. So in that case, V will T and P. So you can write like this as well, which will be now del V, del TP, del T, del PV, and del P, del V T. This is also -1, and these two equations are same actually. You can convert it. Okay, so that was the whole thing. N is not considered here because N we have considered for 1 mole of gas. That is the reason. Okay, so now we can discuss one example regarding this. Cyclic rule. So let me write it. Using the cyclic rule, so that the coefficients denoted by alpha and beta are related as alpha equals to beta times gamma p, where alpha equals to 1 by v, del V del Tp, and beta equals to minus 1 by V del V del P T. At gamma, 1 by P del P del Tv. Okay, so these are the three coefficients. So now we have to just establish this relation, right? This relation we have to establish right now. So for establishing this relation, we will use the cyclic rule, obviously. So now what we have identified here, that yes, so these three things are there. Okay, so what we can write that from the data, that alpha equals to 1 by V del V del Tp, which essentially means that del V del Tp is actually the alpha times V, that we can write here. Next, what we can write, beta equals to this one, that means 1 by minus 1 by V del V del Pt. What does essentially means that del V del Pt is equals to minus beta times V, and at the last it is gamma is given, which is 1 by P times del P del T V. So from here we can write that del P del T V is gamma times P. So now from here, what is the cyclic rule we can formulate, that you can see here. So there are three variables, V, T and P. Three variables are there. So from there we can write V as a function of T and P. So if this is true, then what will be our cyclic rule? We know that we have to write it like this way. So cyclic rule will be del B del Tp, then del T del Pv del P del V T equals to minus 1. So just we have to now replace these things. First, del B del Tp. So this one, it is alpha times V. Next, del T del Pv, this one. From here we can write that del T del Pv is essentially 1 by gamma P. So it will be 1 by gamma P. And the third one, del P del Vt. From here you can write del P del Vt is essentially 1 by minus beta V. So it is minus beta V. So that is minus 1. So minus will be goes away. V will be cancelled. So from here it is clear, alpha equals to beta times gamma P, and we have to prove that this one, beta times gamma P. So hence it is proved. Okay, now the next question, it was question number 3. Okay, so let me write the next question first. So before discussing the next question, okay, so let me first discuss this, then we will go to the another topic, that is Euler's reciprocal. Okay, I will come in. So that del P del T V, this question is also related from the previous one, which is alpha by beta. We have to show it. One thing we can do here, that we know what is alpha and beta, that alpha is 1 by V del V what? Del V del Tp, and beta is minus 1 by V del V del Pt. How you can remember these things? What is alpha, what is beta? These things will be remembered. 1 by V is here for both cases, and for beta it is negative always. It's correct. But how you can remember that? For that you can use this trick, that we know beta is always related to temperature. Okay, you know from the Maxwell distribution or Boltzmann distribution that in general we use beta essentially signifies that 1 by kBT. So beta is always related to temperature. So in case of beta, the temperature will be constant. In that way you can remember. Although this beta and that beta are different, in that beta is called inverse temperature, which is actually 1 by kBT. But here this beta is not inverse temperature. This beta is obviously the compressibility factor coefficient. So okay, so you can put it and we can do it, but we have to prove this equal to that. So we have to start with this. So del P del T V. So clearly we can write the cyclic rule. What will be the cyclic rule? Del P del T V del T del Vp, then del V del Pt equals to -1. So from here you can write del P del Tv, which is our left hand side, is essentially equals to -1 divided by del T del Vp del V del P T. So it will be essentially minus del V del Tp divided by del V del Pt, or you can write it like this, and you can add 1 by V here, 1 by V here. So essentially it will be alpha by beta. In that way you can write it. Okay, and you are writing, you can write this as a this, that essentially means these are exact differential, right? I will come into that. For in case of exact differential only, you can write as, okay, I will come discuss that in the next question. So this is clear, right? So our next question is question number 5. Define the exact differential. Okay, this is very important thing. We have to define what is called exact differential. Okay, and this is related to one concept, that is, we will discuss Euler's reciprocal relation. That is very important. This essentially dictates what is called the exact differential. So the base, in general definition of what is the exact differential, let's say z is a variable of x and y. If z is a variable of x and y, then if you can write dz as some function of xy. Okay, what I want to mean that like this xy type, then it is called the exact differential. It should not be xy, it may be x squared y, xy square, something like that. You have to write it in that fashion, then only you can say this is called exact differential. This is our the formal definition of exact differential. So I want to mean that you can write it as x to the power n, y to the power n form, where n is actually minus infinity to plus infinity, an integer. So in that case it will be called an exact differential. So this is the formal definition, you can say. So just like you can take an example, like it may be like dxy square or dx square y, or it can be dx to the power -1, that means x by y. So if you can write this as, then you can say this is an exact differential. But if you have to find out whether it is an exact differential or not, for that it is better to check this Euler's reciprocal relation, then you can check it easily. So how to do that? So if z is that, then you can write dz as partial derivative del z del x constant y dx plus del z del y at constant x dy. In this manner you can write it. And now let term it as n and n, so you can write it as m dx plus n dy. So it will be an exact differential if and only if, you can say, if it is followed that m del m del y at constant x is equals to del n del x at constant y. If this is followed, then you can say this is an exact differential. Okay, so this is the criteria. Okay, but how you can write it more simply, or you can learn other way of writing. You can think like that. What is m here? So m is actually del m, del z del x constant y. Already you have selected it here, and then n was del z del y constant of x. So essentially this is nothing but del y of del z del y constant of x, and this is constant of, this is x, right? Constant of x, and this is del x of, what is n? N is del z del y constant of x, and this is constant of y. So this is the another form of writing. Okay, so in that case, in shorthand notation you can write it del 2z del y del x is equals to d2z del x del y. So this is actually the called Euler's, the same thing. Relation. So if this is valid, if this is followed by any differential, then it will be called, the differential will be called an exact differential. That's the basic definition. Okay, so the example we will follow, we'll do it next. But what is the physical significance of this? That we have to understand. That is very important to understand the physical significance of the exact differential. Let's say I am saying that this is an exact differential. What does it mean? So we can say if dz an exact differential, if we can do the exact differential of that variable z, then we can say that z is a state function. So essentially z will be dependent on the independent variables only, x and y. Here you can say it is not depending on the path. Let's say we are changing x1 y1 to x2 y2. Okay, so essentially this will signify a value z1, which is essentially will be function of x1 y1, and this is signifies to z2, which is a function of x2 y2. But if dz is an exact differential, then obviously this z1 and z2, this will be dependent on the values of x1 x2 x1 y1 and x2 y2, not the path. Okay, so what is the dz? So dz is the just difference, z2 minus z1. That is the case. In which path you are going, that will be not important. So we can understand this just using a figure or diagram, then it will be easier. So now we are defining a variable z, function of xy, just this. So we can check whether it is an exact differential or not. Let me check. So how we can check that? We have to find out that del 2z del x del y. So first we have to find out del z del x constant of y. So it will be del x of this. Okay, so we can write, let's say x square plus y square is as u, so it is just u root over u. Obviously y is constant anyway, that I am not considering here. So I can write, okay, and u is obviously x square plus y square. So it will be u to the power minus half, right? So root 2u, and it will be 2x, straightforward, correct? So it is actually x by root over x square plus y square. So it's easy to say that del z, sorry, d2z, or we can directly write it from here. This will be essentially y by root over x square plus y square, correct? That's easy. So now what is d2z dx dy? That will be del x of del z del y, constant of x, and then constant of y. So first term is essentially y by x squared y square, and now y is constant, so you can take y out, and then ddx of 1 by root over x square plus y square. So we have to do it again. So y, and again let's say this is v, it is del v of 1 by v and del v del x, and v is again x square plus y square, or it is actually u because we have already defined it as u, correct? So it will be now minus half and 1 by u to the power 3 by 2. Okay, is it okay? And del y del x, so del y del u del x, so it is again 2x, so it is minus xy u to the power 3 by 2, means x square plus y square to the power 3 by 2. So this is our d2 z del x del y. Now similarly we can calculate the other term del y del x. So it will be now, so does it mean that del y, this is del x, constant of y, and then it is constant of x, right? So this term is known del z del x, this is, so it is eventually the del y of x by root over x square plus y square, and now the constant part is x, correct? So now x will be coming out, so it is del y of 1 by root over y square plus x square when constant is x. So you can carry out this, let me do it. So this is del u 1 by root u and del u del y, correct? And del u del y, u is actually x square plus y square, so it will be again x into 1 by u to the power 3 by 2, this, correct? Minus half will be there, and it will be, if I'm not wrong, so it will be 2y. Okay, so this is, then from here you can write it is as, what will be this, x y u to the power 3 by 2, means x square plus y square to the power 3 by 2. So it is same. So from here you can see what you can conclude, that okay, so it is eventually an exact differential. You can see that this is not just x to the power n y to the power n form, right? But also this is an exact differential. So this is not in general true, I was just discussing that, but actually the main the rules is you have that you have to follow the Euler's reciprocal relation. Here it is following this, so it is an exact differential. Okay, so I am taking this kind of difficult example, but to give you a graphical representation, let's say. So now we have x and y, correct? And we know z is defined as root over x square plus y square. Okay, so take first value. So this, let's say, so this is actually 0.22. Okay, so what is the value of z here? So this is actually, let's for this point 22, z is actually z at 22 point, z is then it is z1, which is function of x equals to 2, y is equal to 2, which will be now root over 8, which is 2 root 2. And let's take this point, this is actually this point 5 5. So again it will be z2, which will be x equal to 5, y equal to 5, so it will be 50, so 2 root 5. So these are 2 points. So we have z1 and z2. So if you want to calculate the dz means the distance between, the difference between these 2 points, so that will be eventually this, if I want to say. So this, so you can see this dz, it should be invariant over the path, because we are saying that is exact differential or state function, so that we can check whether it is correct or not, dz is correct or not. So now what will be, let's take the first path, which is going like this way, in this fashion. So here you can write, we know dz actually is del z del x y into dx. So you can see here in this path, up to this point to this point, the x is varying, y is constant, so this is into dx, and this is signifies this part. Okay, so that's why these are added up, obviously, for this path. Okay, so if you do it, so this is the definition. Okay, so now if you calculate the other, consider the another path, let's say this path, this is path 2, or you can follow any other path, just like this path you can follow. This is our path. So any path you follow, this definition will be same, so it will be a, so you can calculate it, you have del z del s, everything is known, so you can calculate it, and you can check for each and every path. If you calculate the dz with this formula, just I have reused this formula, it will be the same, so it will be a state function. I am not doing it, I will upload the note, because it is just a calculation, you can check it. So if there is any doubt again, after reading the note, then we can discuss in the next class. But this is straightforward. What I am saying that you can choose any path, it should not be in that way quantized path, you can think any path. For each and every path it will be the same, dz will be the same. So why it is happening? Because z is an exact differential, so that is why it will be a state function. So it is the ultimate conclusion is that for state function, exact differential, it will be a state function, it will be only dependent on the initial and final stage from here to here. This is important, it is independent of path. Okay, that's the reason why equilibrium thermodynamics works, because as we have discussed here, what here, so for reversible process only the equilibrium thermodynamics is allowed, but for irreversible process the non-equilibrium, we should follow the non-equilibrium thermodynamics. But actually you don't do. In our regular life we know that equilibrium thermodynamics is actually the basic thermodynamics which we use to develop variety type of machine or other things, which actually follows this equilibrium thermodynamics. But how this works, although this is reversible process, quasi-static process, these are totally hypothetical, this is not realistic process. In reality irreversible process is happening, there is a dynamics that should follow the non-equilibrium thermodynamics. But where is the catch? Let's say one state is changing from initial stage to final stage through a reversible path or a irreversible path. It is independent, the change, if it is a state function, let's say any state function x, xi and xf, So del x, which is a difference of xf minus xi, this will be the same for both path. So del x irreversible should be equals to del x reversible. So that's why you can follow the equilibrium thermodynamics, this formalism, because it will give the same result if it is non-equilibrium, if it is follows the irreversible path also, because these are the state function. So that's why we are dealing with the state function always. In case of path function, you will see this will not be the same, there will be trouble. In that case, trouble will appear. Okay, so that's why our equilibrium thermodynamics works fine. And you have also heard that for our classical thermodynamics, in this course what we are going to study, the difference of the variable state function is important, that I have mentioned here. The del x is important because it will be same for both paths. The difference will be the same. So that is actually the outcome of the state function property. Okay, so now we will do some example of this exact differential. It is question number 6. Okay, so now I'm writing df what are the options? Okay, so it is clear this is not an exact differential. Eventually we have the form of dz, and we know when we have the form of df anything, so we know this will be follow mdx plus ndy form, and we have to show that del m del y at constant x equals to del n del x constant y. So it is clear that here no mdx part, so it can't be an exact differential. It is not. Okay, it is also not. Here both is there, but there is a negative sign, so it is not an exact differential. Here what is am is 1, so it will be 0. So again it is not, so it will be an exact differential. You can see, check where what is the m here. For option D, m is 1 by y and n is minus x by y square. So del m del y at constant x is minus 1 by y square, and del n del x at constant y, it is also minus 1 by y square. So it's matching. And also you can say, identify that what you can write. So df is that, so obviously f will be x by y, then only df is d of x by y. So d of x by y is eventually 1 by y dx plus it's okay. So now what, x d of 1 by y. So what is the d of 1 by y? How you can identify this d of 1 by y? So it is eventually d of y to the power minus 1. So let's say, so d of y to the power minus 1 dy it is eventually minus 1 by y square. Okay, so you can write it, d of y to the power minus 1 is minus 1 by y square dy. So it will be 1 by y dx minus x is there, it is x minus y square dy. So the same form. Okay, so this is x to the power 1 y to the power minus 1 form. Okay, okay, nevertheless, next question, question number 7. We have to check whether it is an exact differential or not. So now it is our m, it is our n, and we know we have to check del m del yx, right? So what will be that? 51x square plus 47 into 4 y cube. So it is 51x square plus 188y cube. Okay, and the next part, del m, sorry, del n del x y. So what will be that? 17 to 3, it is 51x square plus 188 y cube. So it's matching. Okay, so it is evident that dz is a exact differential, right? So now here also you can show that dz as a function of some x to the power n y to the power n, in that fashion also you can show. Okay, but that is not trivial here because the form of dz is not very much straightforward, but from this Euler's reciprocal relationship you can surely comment on that it is an exact differential. Okay, so now the next question, question number 8. Okay, it is, so we have to show that del alpha del pt equals to minus del beta del tp, and we know what is alpha and beta, that was already known to us, that is 1 by v del t p, and beta is minus 1 by v del p t. So now we have to show it. Okay, how we can show it? So here what we can write, del alpha del p t, first one. So eventually it will be 1 by, no, two things are there, right? So temp, we have to differentiate with pressure, and 1 by v is also there, so it will not be that much straightforward. Okay, what should we do now? Okay, we can do in this way also otherwise, because it is xyi. Okay, let us do, let's see what happens. So now we have to first, we are doing del alpha del p at constant t. So it will be del p 1 by v at constant t. This first part will be there, this will be considered, and in that case del v del tp will be there, it's constant, and then 1 by v will be there, and it will be d2v del t del p del t, right? It's clear. Okay, now we have to tackle this part. How you can do it? This can be written as, so this part we can write like this, minus 1 by v square del v del pt into del v del t p plus 1 by v d2v del p del t. Okay, is it clear, Naito? Okay, I think it's clear. Now the second one, what is del beta del tp? Similarly, we can write it del t of 1 by v. Obviously there is a minus sign here now, and here will be p, and del v del t p will be there, this one. Oh sorry, beta में pt है, sorry, so del p t plus minus 1 by v into d2v del t del p. So this is the case. Again we can write it as, this will be now 1 by v square del v del t p, this is again del v del p t minus 1 by v d2v del t del p. And we know that v is always an exact differential of function of p and t, and it's a state function, so it will be an exact differential. dv will be an exact differential. So as dv is an exact differential, so you can write d2v del t del p equals to d2v del p del t. That is important here, because it is an exact differential. These two terms are same, this term and this term are the same. Okay, so and del v del pt del v del t p, 1 by v square is there, so it is evident. If you compare to equation here, clearly it can be written that del alpha del pt equals to minus of del beta del p del tp, because here is a minus, here is plus, plus minus. Okay, so it is clear. Okay, so it was our question number 8. Now going to our next question, which is question number 9. Check. Okay, volume is an exact differential or not for ideal gas. That we have already stated there, that volume is an exact differential, because volume is a state function. That's why you can say it safely that volume is an exact differential. But you can also establish it from here, from ideal gas equation, which is P equals to nRT, right? So for 1 mole of gas, we can write it V equals to RT by P, 1 mole. Why I am writing this? Because you know, in that case only, oh sorry, what is this? Oh sorry, in that case only V can be written as function of T and P, two independent variable. Otherwise you need n, that we have already discussed. So here we are taking n equals to 1, so V equals to RT by P. Okay, so in that case what you can write, so now it can be written as, what we have to check, that del V del Tp equals to del P del Tv del 2V, that Euler's reciprocal relation, you have to check whether it is being satisfied or not. So it is actually del T del V del Pt, and this is at constant V. So this we have to check. The first part, this part, del V del Pt, what will be this? From here it is clear that it is actually minus RT by P square. Clear? So just put it. So del T minus RT by P square at constant V. No V is there eventually, so it will be just minus R by P square. Now the another part we have to calculate, which is del to V del P del T, which essentially signifies this. Okay, so this part del V del T P from the ideal gas equation, it can be written as R by P. So it can be, so just put it, again it is minus R by P square. So both are matching, equal, so you can write okay. So it means that it follows Euler's reciprocal relationship. So that's why it can be said that V is a state function and also is the differential. Okay. Okay. One thing it can be clear here, if it is considered as P equal to nRT, let's say, what will happen then? Because then N will be there, correct? If it is not a 1 mole gas, then we have to consider N as constant. If N as constant, then we can write these things as well. Then it will be only function of volume and temperature. So in that case, you can easily bring out N. So again, it will be N here. N will be there, right? N will be there. So it will be N by P square. Similarly, here will be N. But if N is not a constant, then you will be in trouble. Not trouble basically, then you have to write down that V is a function of N, T and P. Okay, if that is, then dV will be del N, del V del N Tp constant dN plus del V del T Np constant dt plus del V del P Nt constant dP. So 3 terms will be there. Okay, 3 terms will be there, and it is an exact differential, right? So ultimately you can show that it will be del T del P del N equals to del 3V del P del N del T equals to del 3V del N del P del. Okay, 3 will be there first, because here also the cyclic rule should be there. NPT, so N we have written as NPT PTN. Okay, this will be PTN and TNP. So these 3 will be same. You can show it here also, you can prove it. Just first you have to take the derivative with pressure, then N, then just it's not difficult, and it's also linear to N, so you can show it also. But it's better to not get into that. For that we can easily use this equation, PVM equals to RT. This is more useful here, where V is our molar volume. That means Vm equals to V by M. So then it will be very easy. Okay. Now the next question, this is also related to this, so that again pressure is a state function for a gas obeying a relation which is P plus A by V square into, sorry, not V square, Vm square into Vm equals to RT. So it's not totally van der Waals gas, it's kind of van der Waals gas it is. So you have to show it, where Vm you know is molar volume V by N. So it is P plus A by RT, correct? So from here you can write it P equals to RT by Vm minus A by Vm square. Now you have to show that pressure is an exact differential. So for that you have to establish del P del, because now pressure is a function of T and Vm. So you have to show Vm dt equals to this. You have to show it to prove it an exact differential. So now the first term, let's say, so this is eventually del Vm del P del T at constant Vm constant T. So now del P del T Vm, what will be that? If you differentiate it here, no T, so it will only be R by Vm. So just let me write it here. At constant T, and it will be now minus R by Vm square. Okay, now the second part, it is actually means that okay, so del P, you have to take derivative of P with respect to Vm. So now it will be del T of, first term will be minus RT by Vm square after taking derivative, and the next term will be, this will be plus 2A by Vm cube. I think it's clear. Just derivative I have done. It is Vm, now we have to take Vm constant. The first term will give minus R by Vm square, and second term will give 0 because that is not T term. So essentially it is matching, it's same, it's same. So it's an exact differential. So we can write that therefore pressure is a straight function, right? Correct. Okay, this is question number 10. Going to question number 11. Prove that, prove the cyclic rule from PVM equals to RT. You have to prove it. Okay, let's check whether it is following or not. Okay, so now how we can prove it? Just have to write the cyclic rule in terms of PT and Vm. If you write the cyclic rule, it will be del P del T Vm del T del Vm P it should be equals to -1. That we have to show. The first term here, what you can write, del P del T Vm. What should it be? Because P is equal to RT by Vm, so it is R by Vm, right? Next, del T del Vm P. So it will be, because T will be here, P Vm by R. So it should be P by R. And the last one, Vm is equals to RT by P. So del Vm by del P, it should be minus RT by P square. So if you write it here, put it here, so then it will be R by Vm into P by R. It is correct, I think. And then it is actually minus RT by P square. So it means it is actually, okay, these R will be cancelled. So it is RT by PVM, right? One P will be cancelled, and again you can put RT equals to PVM, so it will be PVM by PVM, so it is eventually -1. So it is following the cyclic rule. Okay, so question number 12. An arbitrary variable, let's say phi, is found to have following relation, which is d phi equals to RT by P dP minus R dt. So now check whether phi is a state function or not, and calculate this. Okay, no, it is that check is 0 or not. Okay, so how you can check it? First, d phi is given, so d phi is actually RT by P dP minus R dt. So here it's clear that phi is actually function of T and P. So that's why it can be identified as, this is actually M, this is N. So M is actually this, and N is minus R. So therefore we have to check del M del TP here, okay, because their P derivative is already there. This is will be now R by P, clear, it's R by P, and it should have to check del N del PT, it is 0 because R is a constant, so clearly it's not matching. So therefore del M del TP, it's not equals to del N del PT. So therefore what you can conclude from here, that d phi is not an exact differential. Okay, so therefore phi is not a state function. Now if phi is not a state function, then this should not be 0, because you know for state function only, because for state function, let's say if phi is a state function, then you can write it as some cyclic path. Cyclic path means A to A. Let's say you are starting from A, you are going to B, and again you are coming back to A. So for that you can write it for same state to same state. This is, so it is actually phi A to A. So that means it is phi A minus phi A. So it will be 0. But it is not a state function, so it will depend on path. So it not equals to 0. Okay. Now the last question what we can discuss here, probably it should be the last question. Let me check. Okay. Among the W, which is work done, Q, which is heat, U, internal energy, which is a state function. It's very clear. This is just MCQ type of question, which is a state function. Okay, so internal energy U is a state function. Because you follow the du is an exact differential, Q and W is not. That's why from first law of thermodynamics you know that what we write in small, in case of small change, this is written as du is equal to d cross Q plus d cross W. Cross is given because this is not an exact differential, or in large scale this is just Q plus W from the first law of thermodynamics. So it's clear that U is an exact differential. Okay, so let me stop here today. So we have discussed this question, 13 question today we have discussed. In next class I will basically first I will discuss the equipartition theory that I have thought to discuss today, but due to these technical glitches and all these, the time actually don't permit me to discuss this. So I will discuss in the next class first, then we will discuss the rest of the things which will be discussed in this week, in the classes are uploaded in this week. Okay, so let me stop here today because this is the recording part. I have recorded this part later, so please go on through this part, and if there is any doubt, extra doubt, you can ask me in the next class. Okay, and in live class I have taken the doubts from the students who had attended these classes, but due to the technical glitch I did not record that part. Okay, that's why I have recorded this part. Probably now it's totally fine, and I have loaded the total class which I have taught in the live class, and I have recorded this, and I will upload this in YouTube, and you can go on through the whole tutorial lecture, and from this lecture or the lectures uploaded by the NPTEL of that course, from there also if you have any doubt you can ask me in the next class. Okay, so let me stop here today, and thank you for listening. Okay, so let's meet again in the next class. Bye.